Imagine a galaxy where time has slowed to the crawl of old light. No spiral arms, no neon birth clouds, just an elliptical halo the color of cooled amber, built from ancient, metal-poor populations whose spectra line up like fossil pages, strong MGB, weak H-beta, alpha-enhanced ratios betraying a star formation burst that quenched long ago. Velocity dispersion, not rotation, holds the system together. Random stellar orbits smear structure into a smooth spheroid, the red sequence textbook-made sky. Deep imaging shows a faint catenary of tidal fluff, ghosts of mergers that finish the chemical enrichment and shut the gas valves through feedback and exhaustion. ALMA finds little CO, GALEX sees only a faint UV upturn from hot horizontal branch relics, and integral field spectroscopy maps a core with anemic line emission, as if the interstellar medium forgot how to collapse. Now tune the instruments tighter. Around a quiet, long-lived red subdwarf in the outskirts, a rocky super-Earth circles inside a temperate band where irradiance drifts only slowly over gigayears. Its atmosphere is thin, aerosol-rich, photochemistry-dominated. Haze particles loft along the limb and flatten alkali absorption, muting Na-D and Ki as transmission spectra slide toward a smooth, gray slope. Phase curves in the mid-infrared whisper about a high dayside, nightside contrast and a boundary layer that conducts heat reluctantly. Polarimetry at crescent phases stiffens, consistent with submicron grains compacting in a dry upper sky. The planet's mantle cools under a star whose variability is kinder than a sunspotty youth. Fewer flares, long stability windows, a geological diary that can afford to write slowly and in detail. On the edge of the frame, a globular cluster hangs like a sealed vault. Color magnitude diagrams pin its age to the dawn of the host, turn-off points low, blue stragglers sprinkled by stellar collisions, a horizontal branch stretched by helium spreads and rotation. Proper motions knit thousands of stars into one dynamical organism. N-body models recover a dense core primed for close encounters, the kind that swap companions and light up X-ray binaries at a trickle. Tidal tails leak from the cluster's Roche lobe, tracing the galaxy's potential. Follow them and you read the mass profile without ever seeing dark matter directly. Put it together and a method appears. Use NIRSpec and MUSE to decompose the integrated light and age date the stellar archive. Pair ALMA non-detections with dust limits to bracket how dead the star-forming engine really is. Hunt the super-Earth with high-resolution cross-correlation. Stack nights until molecules emerge from the noise. Chase polarized glints near superior conjunction to weigh haze opacity. Time the cluster's tidal debris to calibrate the gravitational field enclosing everything. In a place where new stars scarcely ignite, physics gives you other candles. Kinematics, chemistry, thermodynamics, all still burning, all still legible. If you want to know how worlds endure when a galaxy goes quiet, you start here, in the amber, where memory is luminous and change is slow enough to measure. Imagine an island of old light, a galaxy that long ago traded spiral exuberance for patience, its structure smoothed into an elliptical body whose color leans toward cooled resin. The spectrum is a palimpsest of finished stories, strong magnesium lines, a depressed H-beta, calcium triplet shoulders that rise like worn hills, alpha-enhancement that fingers a fast, intense early epoch when massive stars died in crowds and then the engine fell quiet. There are no arms to guide you, only the statistics of motion, velocity dispersion dominating over ordered spin, isophotes nearly concentric but whispering of past violence in their faint twists. If you stretch exposure time until the sky background becomes a granular texture, filaments and shells begin to appear, tidal archaeology from a merger sequence that delivered both metals and exhaustion. The galaxy joined the red sequence not with a single decision but with a chain of feedbacks, starbursts that heated and vented the gas, a black hole phase that overpressurized the halo, and the slow arithmetic of consumption with no external replenishment. What remains is a system where time is measurable in the thinning of the ultraviolet upturn and the drop of specific star formation to a number that can be confused with zero. To say, there is no gas, is always an approximation. Pockets remain, tenuous and warm, dust survives as a low-opacity veil. ALMA maps that look almost blank still constrain the reservoir to a few million solar masses spread so thin that gravitational collapse is less a forbidden act than an unlikely coincidence. In the ultraviolet, a population of hot horizontal branch and post-AGB stars fakes a memory of youth, the so-called UV upturn, reminding us that old age in galaxies is complex. Integral field spectroscopy stitches together a quilt of line ratios across the core and out to effective radii, low ionization emission hinting at shocks and the gentle photoionization of a background field rather than the respiration of newborn clusters. The mass-to-light ratio creeps upward with radius, and when you invert the stellar kinematics you find a dark halo heavy enough to keep everything bound, a silent partner whose only signature is how fast stars forget where they were headed. Somewhere in that amber sea, far from the busy center, where tidal fields grow polite, circles a red star that has outlived expectations by never being asked to do much. Its mass is lower than the sun's, its convection deep, its rotation slow, its light curve is an exercise in calm. Around it travels a rocky world that measures about twice Earth's radius and several times its mass, dense enough to bully hydrogen from its exosphere, old enough to have settled into a mature tectonic rhythm. The atmosphere is more suggestion than presence, a thin film of gases regulated by a surface reservoir of minerals and a modest inventory of volatiles locked in crustal pores and polar cold traps. Photochemistry on the day side manufactures aerosols out of silicate vapor and oxidized fragments of carbon delivered by micrometeorites. These grains loft along the limb and flatten the way sodium and potassium would otherwise bite the spectrum, turning sharp lines into a slope. If you watch the planet through an infrared band that follows heat, you see the dayside surging and the nightside lagging, a phase curve whose amplitude says the boundary layer is stingy with energy, that the atmosphere, such as it is, prefers vertical motions to horizontal wind. At crescent phases the scattered light becomes more organized, polarization climbing as grains align or compact. That modest, orderly flash is the signature of a sky that has learned to be economical. Geology under a red sun is a long conversation between heat sources that decay and a mantle that refuses to rush. Radiogenic elements that dominate on gigayear scales, uranium, thorium, potassium, insist on a slow simmer, while the original accretional heat has faded to memory. Without a massive moon to knead it and with a quiet star that does not hammer it with extremes, the planet lets continents grow thicker before they founder, recycles plate edges in stately cycles measured not in tens but in hundreds of millions of years. Basalts extruded in earlier epochs weather into thin soils that trap little carbon, carbonates precipitate in lacustrine basins when occasional warmth and pressure align, serpentinization in fracture networks produces hydrogen that never meets much CO2. The redox budget of the crust drifts toward neutrality, and with it the atmospheric composition drifts toward minimalism. There is water, but more in rocks than in rivers, more as adsorbed films in regolith than as oceans. When impacts deliver new packages of volatiles, the planet exhales briefly, frosts thicken, haze deepens, then the surface rehides the bounty. Detecting such restraint is an art of stacking small signals until they cohere. High-resolution spectroscopy uses the rotation of the world as a Doppler comb, cross-correlating a noisy spectrum against templates of expected molecules. Nights stack upon nights, and the correlation peak grows like a ghost finally deciding to commit to being seen. Photometric monitoring over many orbits builds a phase function that cares about grain size more than gas identity. Add polarimetry and the degeneracy between particle shape and vertical mixing begins to relent. Secondary eclipse, when the planet tucks behind its star, subtracts the star alone from star plus planet and leaves you a thermal fingerprint you can integrate for hours. Eclipse mapping teases out longitudinal structure, no continents yet, but hints of how fast the air can move heat. If the system is inclined just so, occultations by small bodies in the host's debris population occasionally sketch diffraction fringes in the light curve. From those you can place limits on the population of dust and the survival of planetesimal belts in galaxies that retired early. The star, though quiet by the standards of youth, still breathes magnetism on cycles measured in decades. The chromosphere warms and cools with modest amplitude, flare rates are low enough that the planet's exosphere can rebuild between events. Cosmic rays from the wider galaxy are moderated by the star's heliosphere, and the galaxy's own cosmic ray background is lower here than in a starbursting spiral's lanes. Over long arcs of time, this relative gentleness imprints itself on atmospheric escape rates and on the chemistry of the upper air. A coronagraph tuned to the stellar Lyman alpha line searches for hydrogen tails and finds only the faintest suggestion, a world too heavy, too cool, too frugal to waste its lightest atoms quickly. Sodium and potassium, usually theatrical in hot super-Earths, lurk in muted profiles, consistent with a haze optical depth that converts sharp features into a pleasant monotone. Carbon-bearing species hide below the detection threshold, or else they are bound in rock. The planet is not devoid of weather, it is instead a place where weather has learned to keep secrets. On the periphery of the scene, a globular cluster hangs with the calm of something that has already won the long game. Its stars crowd a core that would make a city planner cry. Encounters are frequent enough that binaries are forged and broken like soft treaties. The color magnitude diagram drawn by a patient observer tells you the age, main sequence turn-off faint, subgiants queued neatly, red giants thick along a branch, blue stragglers punctuate the distribution, evidence of collisions and mass transfer that grant temporary youth to otherwise ancient systems. The horizontal branch stretches, its morphology betraying helium spreads and rotation fingerprints. Proper motions recorded over years unspool into elegant loops. When you combine them with radial velocities you arrive at three-dimensional orbits that talk more clearly about the galaxy's potential than any photometric profile could. From the faint tidal tails that leak away from the cluster's Roche lobe, you can back out where pericenter passages were and how the enclosed mass changes with radius. The cluster is a chronometer. It is also a seismograph, registering the faint tremors of a gravitational field you cannot otherwise touch. If you want to weigh the black hole at the galaxy's heart, the remnant of mergers and accretion you cannot see directly because it has long since gone quiet, you can do it by letting stars do the reporting. Near the core, velocity dispersion climbs, and subtle departures from Gaussian line-of-sight velocity distributions betray an unseen point mass. Schwarzschild modeling builds families of orbits that can reproduce the absorption line kinematics. The preferred models include a central mass whose sphere of influence is small but not invisible. The same data, pushed into higher signal-to-noise with integral field units, tell you whether the core is scoured by the ejection of stars from hard black hole binaries, whether the light profile flattens into a core that remembers a violent history. You do not need fireworks to prove an engine, you need only the patience to read motion. Chemical abundance patterns carry the accent of the past into the present. Alpha-enhanced ratios point to a quick build-up by core collapse supernovae before Type Ia events had time to supply iron. Sodium and aluminum trends reflect the multiple populations that globular clusters famously harbor. Calcium and titanium track the massive progenitors of the earliest days. Radial gradients in metallicity flatten as you move outwards, testimony to mergers that stirred what disks would have stratified. When you measure these gradients in integrated light, you integrate not only over radius but over time. Every radius has been many radii in its life, every orbit a vector sum of departures. The interstellar medium that remains drifts through phases that rarely touch star formation thresholds. Hot gas, heated by the deaths of the last AGB winds and the few supernovae that still occur, percolates through an X-ray emitting halo. Warm gas traces shocks from old gravitational scuffles and occasional infall of satellites whose gas is stripped before it can do anything creative. Cold gas is present mostly as a rumor that dust would like to confirm but cannot. Without fresh inflow along filaments, the galaxy is a closed vessel, its metallicity creeps, its dust sputters against hot electrons, its future is a study in asymptotes. Place the planet back into this environment and ask what it means to grow old in a quiet universe. The absence of nearby supernovae for hundreds of millions of years reduces bursts of high-energy radiation that might strip an atmosphere or rearrange its chemistry. The steady, low background of cosmic rays sets a floor under ionization that can sustain fragile layers of charged particles without tearing them open. The galaxy's kinematic temperature, stars moving with respect to one another like molecules in a warm gas, makes encounters with massive neighbors rare on human timescales, so the planetary system keeps its architecture. Comet reservoirs are not gone, but their perturbations are fewer. Impacts arrive as punctuation marks, not chapters. Geological processes proceed without being reset by catastrophe, and the record they write in zircons and trapped gases becomes the very thing that makes the world valuable, a chronicle with few torn pages. Observation builds from the coarse to the fine. First you establish the host's systemic redshift and velocity dispersion, then isolate a quiet red star with precise radial velocity monitoring that discards the jitter of giants and hunts for the firmness of dwarfs. Transit searches remain optimistic but not required. Radial velocity at meters per second precision in the near-infrared chases a small signal over years. When the orbit is known, you schedule phase curves with a cryogenic telescope that can watch long enough to see heat slosh and stall. You polish those curves with eclipse measurements that, even if shallow, can be stacked across seasons. Polarimetry begins as a long shot and matures into a constraint. The nights are long in the amber galaxy, but so is your attention. In parallel, you invest in the cluster, you map its tails, you anchor its internal dynamics, you let its motions solve for the gravitational field that also tugs on the star and planet you care about. In a spiral, you might reach for H2 regions and young clusters to trace potentials and feedback. Here your proxies are older and finer-grained, but no less truthful. There is room, too, for the unexpected. Ellipticals sometimes host faint, low-luminosity AGN whose radio cores mutter into the interstellar medium, inflating bubbles that remain long after the whisper stops. Those bubbles rise and stir, seeding turbulence that prevents catastrophic cooling. A globular cluster on a plunging orbit might throw off a stream that brushes the planetary system's outskirts with a cometary rain every few 100 million years, a gentle clock that keeps geochemistry awake. A passing dwarf galaxy, stripped of most of its stars, could deliver a small cold cloud that manages to form a few clusters before feedback self-quenches again, writing a brief, bright footnote in a book that otherwise resists revision. When you speak of habitability in such a setting, you must change your grammar. The word does not mean lakes under blue skies and continents explore-ready, it means thermal budgets that do not crash, atmospheres that erode slower than they can be repaired, chemistries that can settle into metastable niches and stay there. It means a planet that can keep records, isotope ratios that drift predictably, noble gases that refuse to leave, rocks that build crystals slowly enough to archive magnetic fields and atmospheric pressures. Life, if it appears, would be a patient accountant, not an engineer of atmospheres. It would stain rocks, not paint skies. Or perhaps life is absent, and the world is still precious, a museum of planetary physics conducted under ideal conditions of time and quiet. Not every experiment in the universe is designed to produce us, many exist to show us the parameter space. The light that leaves this galaxy toward us is old in the casual sense and young in the cosmological one, and in either case it is honest. When you disperse it into colors and measure how those colors change with angle and time, you are reading not metaphors but equations integrated over eons. Velocity fields become likelihoods over mass distributions, spectral indices become posteriors over star formation histories, tiny, repeated dips in brightness become orbits that can be weighed. Even the nothing, the non-detections of CO, the absence of strong nebular lines, becomes data, carving away worlds that cannot be and leaving behind those that can. A quiet galaxy is not a silent one. It is a place where the narrator speaks softly and at length, where memory is luminous and change is slow enough to annotate. So you begin with amber, with an image that looks almost monochrome until you learn to read its gradations. You adopt instruments that specialize in patience, radial velocity spectrographs that accept boredom as a path to truth, infrared cameras that prefer stability to spectacle, polarimeters content with millipercent gains. You find a star whose flicker is small and a planet whose reticence is not refusal. You measure the cluster until you can predict where its outflows will bend, and then you test the prediction against a faint stream of stars you can barely separate from the background. You collect all of these thin, careful lines and braid them into a rope strong enough to pull a story out of the dark. In a universe addicted to fireworks, you practice the science of embers. You let old light teach you what endurance looks like, and you write down the lesson in a script the cosmos has been refining since the day the last spiral arm in this place uncurled and faded. Statistically, the host galaxy sits on the fundamental plane with a Circic index that drifts above 4, its isophotes showing a faint boxiness that betrays anisotropy in the velocity ellipsoid. Genes modeling under axisymmetric assumptions recovers a mild radial anisotropy beyond one effective radius, the kind that results from dry mergers that puff up the outskirts without reigniting star formation. The mass-to-light ratio inferred from stellar population synthesis rises gently when you allow for an alpha-enhanced mixture. When you fold in dynamical constraints, a cored dark matter profile competes with an NFW halo subtly contracted by baryons. Neither choice breaks the story. Both agree that the galaxy's memory is weighted toward mass assembled early and shaped later by gravity's quieter tools. Quenching here wears several fingerprints at once. The starburst epoch drove winds that evacuated the central reservoirs, radial mode feedback from a once louder nucleus inflated cavities in the hot halo, setting up a buoyant cycle that keeps the circumgalactic medium warm enough not to rain. Environmental starvation finished the job. The filaments that once fed cold streams realigned or thinned as the galaxy migrated into less generous real estate. What gas remains cool enough to be molecular lies below the tumor threshold when averaged on kiloparsec scales. Whatever clumps do form are shredded by shear and turbulence before they can collapse. The UV upturn complicates photometry by mimicking youth in broad bands, but spectroscopy refuses the lie. Balmer lines are weak, 4000 A breaks are strong, Lick indices insist on old ages with small metallicity spreads and a clear alpha boost. Globular clusters in this system divide into a familiar bimodality, blue and red, metal poor and metal richer, their spatial distributions tracing different assembly channels. The metal poor clusters wander farther out, dynamically hotter, their orbits more plunging. The red clusters huddle closer to the light, embedded in a memory of dissipative formation. Within individual clusters, multiple populations reveal themselves through anticorrelations in Na, O and Mg, Al, a chemical choreography produced by early self-enrichment and processed material from massive stars. Blue stragglers line the main sequence like mischievous annotations, their overluminosity a record of collisions and mass transfer in a crowded core. Millisecond pulsars tick among them, timing arrays you did not build. Every one of these details is a lever arm on the past. With them, you can pry open how many satellites were digested, how anisotropy evolved, how much of the halo was grown from the inside out versus stitched together from the outside in. The red subdwarf hosting the super-Earth brings its own library of clues. Metallicities in elliptical skew old, but the outer halos commonly include accreted dwarfs with lower metal content and extended star formation histories. If the host star formed in such a subunit before assimilation, its Fe/H may sit slightly below solar while Alpha/Fe remains high, a recipe that biases planet formation toward rocky outcomes by limiting nebular hydrogen capture and promoting refractory solids. High-resolution spectra in the near-IR pick out Fe, Mg, C, Ca lines through the cool continuum. With careful 3D non-LTE modeling, abundance ratios become precise enough to feed interior models of the planet. From the star's Karov ratio you infer silicate mineralogy tendencies. Olivine versus pyroxene-dominated mantles shift melting curves and viscosity, modulating how and whether plates can ever subduct. Inside the planet, compression raises silicate phases to Bridgmanite and postperovskite at shallower depths than in Earth, stiffening the lower mantle and favoring sluggish convection. A larger iron core fraction, plausible in low-volatile builds, increases moment of inertia and the dynamo's options, but a thin atmosphere limits the cooling rate at the surface, and the dynamo's longevity depends on how rapidly the core can shed heat into the mantle. If plate tectonics is rare here, stagnant lid convection may dominate, punctuated by episodic overturns that reset the crust. Those overturns vent CO2 and SO2 in pulses that the haze chemistry chews into photochemical shrouds. Observation can catch the world midpulse if the timing is generous. Volatile delivery by occasional comets shapes the upper boundary conditions. In a quiescent elliptical, perturbations from passing stars are less common, but secular resonances with surviving belts can still cough up icy bodies on mere cadence. Each arrival is a test of escape velocity against ultraviolet compromise. Escape is a slow thief. Energy-limited outflow in the extreme UV regime is muted by the star's mildness. Genes escape at the exobase trims the lightest constituents preferentially, leaving a heavier, drier residue. Without a massive reservoir, hydrogen tails are faint and transient. Photolysis of water adsorbed in regolith porosity supplies a whisper of H that leaks away. Oxygen, too heavy to leave, hides in rocks. Carbon cycles are mineral, not atmospheric. carbonate formation and breakdown in deep metamorphic zones inside a stagnant lid, a loop measured in hundreds of millions of years. Methane, if it appears at all, comes from serpentinization and is eaten by photochemistry faster than it can accumulate. Spectra respond accordingly, a near-featureless Rayleigh tail softened by aerosols, faint mid-IR hints of silicate emission during hot flashes after micrometeor storms, a secondary eclipse spectrum whose color temperature puts the day-night contrast in long relief. Instrumentally, the path forward is unglamorous and powerful. Precision radial velocities in the H-band with a stabilized etalon and laser frequency comb attack the meters per second frontier where cool dwarfs keep their calm. Telluric contamination is modeled with high-resolution Earth-atmosphere atlases and decorrelated with simultaneous sky fibers. Photometry in the mid-IR accepts that the signal is small and leans on systematics control, intrapixel gain maps, rolling band removal, repeatability calibrations that treat the telescope as both instrument and laboratory. Polarimetry revisits its reputation for difficulty and builds confidence by phasing to the orbit, stacking only at the predicted crescent, integrating until millipercent becomes tenths of a millipercent. Retrieval frameworks refuse to work alone, priors from dynamics inform radiative transfer models, mineralogical constraints from stellar abundances bound atmospheric compositions, Gaussian processes capture stellar microvariability without pretending it is weather. False positives haunt every step and must be treated as data rather than embarrassments. Stellar activity at low levels can mimic a planetary RV signal, you counter with line-by-line velocity extraction, looking for correlations with activity indicators that a true Doppler shift will lack. Background binaries in the slit can fake a phase curve, you answer with high-contrast imaging and centroid tracking that nails the photometric photocenter to the primary star. Polarimetric systematics drift with temperature, you instrument calibrate every night on standards and derive a second set of standards from the field stars themselves. When something refuses to go away under this assault, it begins to deserve the name of a world. The galaxy's hot halo is not idle while you measure. X-ray imaging reveals cavities and ripples, the fossil record of a nucleus that once blew bubbles. Those structures imply a duty cycle, energy injected every few tens of mere, buoyant plumes that stir and heat, entropy floors that prevent precipitation. The absence of cool cores here is not a failure but a design, a thermostat that keeps the system parked on the red sequence. Occasionally, a cooling wake does slip through, seeding a handful of compact clusters whose spectra are unmistakably younger, they punctuate the old light with asterisks rather than chapters. You will be tempted to aim at them, you should, but not at the cost of forgetting that most of the story is being told in low contrast and long exposure. On cosmological timescales, the elliptical's fate is to grow faintly larger and ever duller in its colors, its globulars unbound slowly by evaporation and tidal fields, its dark matter halo merging by inertia with neighbors in a dance whose music is gravity's slow drum. The planet and its red host ride that fate like a small canoe on a long tide. If perturbations remain rare, the system will outlast Spiral's pageantry. Its surface will collect micrometeor glass, its interior will tick down its radiogenic clock, its atmosphere will lose a few percent more of what little it has. If a dwarf galaxy falls in along just the wrong vector, the outer system could be stirred, a comet season could bloom, the sky could acquire transient lines that a future observer would misread as metabolism. The universe generates coincidences at a rate proportional to patience. From a modeling standpoint, you will end up building a forward simulator that treats star, planet, cluster, and galaxy as a coupled inference problem. You will propagate uncertainties from the galaxy's potential into the predicted rate of comet injections, you will feed that rate into an atmospheric escape model, you will use the escape model to predict the time evolution of the transmission slope, you will constrain the slope with stacked spectra, you will push the posterior back to update your belief about the potential via the cluster tails, and around it goes. Iteration is not a concession to complexity, it is the only way to make the quiet loud enough to hear. If you want to test interior hypotheses, you will look for seismic opportunities in the star, tiny p-mode oscillations whose frequency separations pin the stellar radius and age, compressing the planet's density error bars. If you want to test the dynamo, you will monitor long-term chromospheric indices and search for rotational modulation that anchors the magnetic cycle, if the planet carries an ionosphere thick enough to participate, you will listen in the meter wave band for cyclotron maser emission near harmonics of the planetary rotation, a whisper of current circuits threading the star-planet space. Non-detections will teach you as much as detections, because they trim parameter space with an efficiency few laboratories enjoy. Eventually, a picture of endurance emerges that is more than romance. It is the practical physics of staying the same long enough to be measured with insulting precision. The galaxy's memory is coded in alpha ratios and dispersion profiles, the cluster's diary is written in tails and blue stragglers, the star's steadiness is a curve with noise you can name, the planet's reticence is a spectrum with features that are small for reasons you can calculate. If life ever tried here, it did so with tools that leave scant signatures, chemosynthetic economies in pores, pigments that never needed to move much air. If life never tried, the experiment remains valuable, because it constrains the prior on how chemistry behaves when time is abundant and energy is sparse. So you keep writing in this amber light, collecting photons that have traveled uncomplicated paths through a medium too earnest to improvise. You accept that fireworks will be rare and that the most dramatic figure you will draw may be a posterior shrinking by a few percent after another season of data. You compile an atlas of patience, phase curves as thin as tracing paper, polarization arcs like pencil marks, spectra that prefer the company of models to applause. Somewhere in those pages the planet becomes not an illustration but an object with a mass, a radius, a heat budget, and a history. Somewhere in those pages the cluster stops being a sparkle and starts being a metronome for the potential that keeps the world in place. And somewhere, between the lines of magnesium and the quiet rise of the infrared, the galaxy that once burned fast explains how to remain, how to be an archive without ceasing to be alive. You can press farther into the archive by letting fluctuations rather than averages do the talking. Surface brightness fluctuations measure the shot noise of red giants integrated over distance. In this galaxy they settle toward amplitudes that lock the distance modulus to within a few hundredths of a magnitude, tightening every dynamical inference downstream. Pixel color magnitude diagrams teased from deep imaging separate unresolved populations by temperature. The tiny drift of mean color with radius resolves into a metallicity gradient that flattens beyond two effective radii, a signature of accretion-dominated outskirts. Stochastic sampling of asymptotic giant branch phases adds a low-level fizz to the near IR. Models that marginalize over that fizz recover an age spread narrow enough to keep the quenching story honest. The initial mass function is the rumor you must verify. Gravity-sensitive spectral indices in the near IR, NAI, CA2 triplet wings, Phe-H, whisper that low-mass stars may be slightly overabundant compared to a Milky Way standard. Dynamical mass-to-light ratios concur but not slavishly, lensing at large radii, if you can recruit a background arc, will arbitrate between bottom-heavy IMF and dark halo tilt. A weak lensing shear field, stacked over many similar ellipticals, supplies a prior on halo concentration. Your object lands within that cloud but favors a profile that is cored inside 1 kiloparsec, either because scouring by black hole binaries has reshaped the stellar distribution or because feedback long ago rearranged baryons and pulled the dark along. None of this matters if you cannot propagate uncertainties. You can, and the ellipse of allowed parameters shrinks with each season of careful light. Globulars choreograph the outermost dynamical dance. Red clusters rotate weakly with the stars, blue clusters tumble in a hotter, more radial ballet, their velocity anisotropy rising with radius. Line-of-sight velocity distributions reveal kurtosis that flips sign where apicenters pile up, fitting orbit libraries reproduces that flip with substructure from two ancient accretion events, one more massive that seeded the blue system, one lighter that sprinkled clusters like punctuation into the halo. The cluster luminosity function breaks where dynamical friction began to matter. In the inner 10 kpc, the deficit at the bright end implies that giants have already sunk and dissolved. Each dissolution event left behind field stars with the same chemistry as their lost homes. You can trace them by tagging Na-O anticorrelations, a fossil map of shredded spheres. The planet sky is a laboratory for opacity in a regime we rarely see. Lab silicate smokes, MgCO3, Mg2CO4, grown under oxidizing conditions deliver refractive indices that, when folded through Mie theory, produce scattering slopes consistent with your observed grayness for submicron grains. If grains grow by coagulation in a thin, calm atmosphere, porosity rises and the single scattering albedo evolves. Polarimetric phase curves at multiple wavelengths can catch that evolution by comparing the location and height of the polarization peak. Thermal inertia, retrieved from phase offsets in the mid-IR, pins the regolith to a mixture of glass and fine-grained rock with sparse volatiles. Occasional spikes, brightening events that repeat with the meteor calendar of the host system, betray micrometeor showers that flash anneal the upper surface into vitreous veneers. After each, emission features near 10 micrometers strengthen briefly before weathering dulls them again. Interior models branch with the star's abundance fingerprint. A modestly supersolar Mg/C with subsolar care of tilts mantle mineralogy toward olivine-rich compositions. Viscosity laws shift the Rayleigh number threshold for mobile lid convection. If the core mass fraction is high, the dynamo's lifetime depends on the efficiency of heat transfer across the core mantle boundary. In a stagnant lid regime, the bottleneck is the mantle, so magnetic activity may be intermittent. Auroral emissions, if any, would be feeble and perhaps confined to episodes following cometary injections that supply fresh ionizable material. A clever radio campaign can fold years of non-detections into upper limits on the planetary magnetic moment, which then feeds back into atmospheric escape models and the allowed surface pressure today. The host star rewards stubborn photometry. Space-based light curves with micromagnitude precision reveal granulation timescales and p-mode oscillations. The large frequency separation delta nu and the frequency of maximum power max triangulate the stellar radius and surface gravity with few percent errors. Those seismic priors narrow the planetary mass and radius into a density that excludes volatile-rich mini-Neptunes decisively. Chromospheric indicators, Ca2HK in the optical, He10830A in the IR, hover low, pacing a magnetic cycle long enough to be annoying for scheduling but short enough to be measurable within a project's lifetime. The star's rotation period, extracted from weak spot modulation or measured via V-sin-I and the seismic inclination, breaks degeneracies in radial velocity noise models and turns a plausible planet into a confident one. Even the nothingness around the star is informative. Deep searches for debris with far-IR photometry set strict limits on cold dust. Non-detections translate into fractional luminosities below 10, typical for austere systems. Scattered light imaging in the optical, pushed to the inner working angle with coronagraphs and post-processing, finds no belts bright enough to challenge the phase curve interpretation. Yet dynamical modeling shows that even a faint Kuiper-like ring could seed sporadic micrometeor flux, an intangible reservoir that only announces itself when the planet's thermal spectrum hiccups after dust falls. Planetesimal dynamics in an old, warm halo prefer secular, not resonant, excitations. Comets arrive as a Poisson rain, not as storms. The galaxy's X-ray halo is a calorimeter that never cools completely. Density and temperature profiles imply an entropy floor sustained by weak, persistent heating. Residual radio emission at the nucleus, compact and flat spectrum, feeds bubbles that rise in the potential, doing PDV work as they go, stirring metals and preventing runaway condensation. Ripples in the X-ray surface brightness travel as sound waves, a low-amplitude metronome that distributes energy broadly. Supernovae from the dwindling old population add a background drizzle of heat. You can budget their contribution and find it insufficient alone, a confirmation that the black hole, even dormant, pays the utility bills intermittently. Kinematics in the inner kiloparsec bear the ghost of scouring. The light profile flattens into a core. Orbital families depleted of low angular momentum stars suggest ejections by a hard black hole binary in a merger long past. Schwarzschild fits allow a central mass sufficient to explain the upturn in velocity dispersion. The sphere of influence is resolved just enough to matter. Gas, what little of it there is, flows without forming a disk. Line ratios land in LAER territory, low ionization emission that has more to do with PAGB photons and slow shocks than with accretion power. You get a black hole that whispers rather than sings and a nucleus that remembers violence without reenacting it. To press uncertainties down, you lean on joint inference. A hierarchical Bayesian model ties together the star's abundances, the planet's spectrum, the phase curve, the polarimetry, the cluster kinematics, and the galaxy's mass profile. Priors on haze particle size distributions come from laboratory aerosols, priors on the dynamical anisotropy come from simulations of dry mergers. Posteriors flow between submodels, a tighter halo potential sharpens comet injection predictions, updated injection rates refine escape calculations, escape histories change the expected present-day Rayleigh slope, the measured slope flows back to nudge the halo again through the cluster tails. Convergence is slow, but the credible intervals shrink visibly, and model comparison penalizes fairy tales that fit one slice of data at the expense of the rest. Calibration is the art that makes any of this possible. Your radiovelocity instrument lives in a temperature-controlled vault, you feed it a comb whose modes are counted against an atomic clock, you monitor intranight drift and remove it with a polynomial that has earned the right to be low order. Your photometer maps interpixel response by rastering bright stars across the detector and inverting the gain field, you adjust for pointing jitter with a decorrelation basis built from telemetry rather than from the light curve itself. Your polarimeter rotates half-wave plates through angles that land on calibrator stars as checkpoints each night, you characterize instrumental polarization as a function of focus and temperature, you propagate that characterization as a nuisance parameter rather than subtracting it like a smudge. When patience pays, it pays in crosschecks. The planet's dayside temperature from secondary eclipse agrees with the phase curve brightness maximum within uncertainties. The albedo inferred from polarized crescents matches the reflectance assumed in the thermal model, the density from RV plus seismology lines up with an interior that explains the lack of a thick volatile layer. The cluster tail model predicts a subtle asymmetry in the star's proper motion over decades, early astrometric hints respect that prediction. The galaxy's mass profile required to bend an opportunistic background galaxy into a weak arc matches the one demanded by the globular anisotropy. None of these alone would be decisive, together they graduate the system from story to measurement. There is a human cadence to the project that sneaks into the data. Winter sees longer, steadier nights for polarimetry, summer grants thermal stability for infrared photometry, years when the star's cycle climbs cost you RV precision but gift you an activity curve that will later become a prior. Students rotate through analyses, leaving behind notebooks that become instruments in their own right, manuals of assumptions exposed and corrected. Pipelines become more conservative as they fail, figures get less pretty and more honest, error bars widen and then narrow because they have learned what they are about. The long thesis of the planet hardens into a paragraph in a broader paper on endurance in red sequence halos. Eventually, you dare to predict. If the micrometeor brightening hypothesis is right, the 10 micrometers emissivity should crest again in roughly 8 years, give or take 1, depending on where a weak secular resonance in the debris ring is now sliding. If the dynamo flickers, a low-frequency radio window will open within a few stellar cycles after a comet season. If it remains closed, your upper limit on core cooling grows stricter. If the cluster's leading tail is where you think, a narrow stripe of slightly metal-poor stars will cross a background galaxy in the field within a decade, imprinting a differential reddening you could measure if you schedule deep exposures before and after. Predictions are not wagers, they are the courtesy you owe a hypothesis before it can be promoted or demoted. What you are left with, after instruments are parked and notebooks closed, is a definition of richness that ignores spectacle. A galaxy with fewer moving parts yields more stringent constraints, a star that refuses drama lets you subtract, a planet that hoards heat and hides gases forces you to quantify ignorance and then take it away piece by piece. The globular that drifts like a lantern on the edge is not an ornament but a ruler, the amber color is not mood but population synthesis in plain sight. The system teaches, endlessly, that longevity is a variable you can observe, in α-enhancement and UV upturns, in core scouring and halo ripples, in thin hazes and stubborn phase offsets. It is astrophysics written in the present tense about things that decided their futures a long time ago, and it invites you to keep reading until the quiet becomes obvious, and the obvious becomes precise. Granularity becomes an ally once you surrender the dream of dramatic features. Climate on a thin-aired super-Earth under a red, steady primary is set by radiative timescales that compete with sluggish boundary layer mixing, the consequence is phase curves whose maxima lead inferior conjunction by tens of degrees when albedo is low and the surface radiates efficiently. You simulate this with a 1.5D energy balance model stitched to a gray radiative transfer core, forcing it with the measured stellar SED and letting the regolith thermal inertia float. Retrievals trend toward low bond albedo, modest heat redistribution, and a thermal inertia consistent with rock glazed by micro-impacts, numbers that would look unremarkable on Mercury but acquire new meaning when integrated over gigayears in a quiet halo. Nightside temperatures refuse to collapse to zero. Conduction through a crust of limited porosity and sporadic katabatic winds carry just enough energy to keep the curve from square waves. Add aerosols and the phase offset shrinks, a reminder that opacity is a thermostat as much as a veil. Tides do little day to day and everything over eons. With a mass several Earths and an orbit that has likely circularized, the principal dissipation lives in the planet's mantle, not in the star's convective envelope. If the world sits just wide of the synchronous radius, because of fossil eccentricity or weak triaxiality, it can sustain a libration that pumps heat episodically into shear zones at the base of its lithosphere. The result is not Io-like volcanism but rare, continent-scale resurfacing events separated by hundreds of millions of years, basaltic floods that briefly spike mid-IR emissivity and toss a fresh load of silicate aerosols into the sky. Catching one of these would be a career's luck. Missing them still constrains their frequency, and the absence of big secular drifts in the phase curve already argues for a world that vents in whispers. If there is a ring in this system, it will not announce itself with theatrical forward scattering, particles in a tenuous, collision-dominated ring around a heavy, slowly rotating planet align into arcs that press us away observational leverage. Yet a ring betrays itself differentially. Polarization spectra taken at matched crescent phases on two epochs separated by a year show a slight blueward growth of the polarization peak, as if the effective scattering radius shifted. You forward model this with a ring inclined a few degrees from the orbital plane and drifting nodes. The fit is not unique, but the exercise tightens the planet's obliquity and argues for a spin state not locked to the orbital mean motion. The ring need not be primordial. Cometary feedstock from a distant belt could maintain it against pointing Robertson drag at the price of a small, steady dust budget that the far IR non-detections barely allow. The star's age is no longer a guess once astroseismology and chemistry converge. A delta nu max pair pins radius and log g, the small separation delta nu 2 calibrates the core's stratification, alpha/Fe, at the surface speaks for a natal cloud enriched early by core collapse supernovae. Feed these into stellar evolution tracks calibrated for slightly subsolar metallicity and alpha enhancement and you obtain an age older than the Sun by several gigayears. Rotational splitting in the modes gestures toward an inclination that, when cross-checked against V sin I, puts the stellar spin axis near the sky plane, an orientation that, combined with the planet's orbital geometry from RVs and phase curves, quietly suggests that the system avoided violent tilting during assembly. Alignment is not proof against excitement in the distant past, but in an elliptical's outskirts it is the default, few giant neighbors to torque, fewer disks to cross. At the galactic scale, you pursue distance and mass with redundant rulers. Surface brightness fluctuations yield a distance modulus you refine with tip-of-the-red giant branch measurements in the most transparent halo fields. The two agree within their systematics, leaving peculiar velocity corrections the dominant nuisance. Stellar kinematics furnish an enclosed mass profile inside a few effective radii. Weak lensing stacks on similar galaxies supply an outer anchor. Globular cluster dynamics bridge the gap with orbits that feel both fields. A toy problem in degeneracy emerges. IMF versus dark halo slope, and you resist the urge to solve it with a single index. Instead you assemble a joint posterior where gravity-sensitive absorption features, Na-I, Fe-H, Ca-I, constrain dwarf fractions while lensing and dynamics police the dark. The answer rejects an extreme bottom-heavy IMF and prefers a mild halo core, the kind that simulations grow when feedback once had teeth and then retired. The globular cluster that ornaments your field is a precision instrument hidden in plain sight. You extract proper motions relative to background galaxies and fuse them with multi-epoch radial velocities into six-dimensional phase space points for thousands of members. Orbit fitting in the galaxy's potential reproduces the S-shaped tidal tails, and N-body forward models predict where density caustics should appear a decade hence. Because those caustics will cross a faint background galaxy near the cluster's path, you schedule deep imaging before and after. If the reddening and surface brightness fluctuations of that background patch shift by the predicted millimagnitude, you will have executed a gravitational dynamics time experiment in a system that most observers treat as scenery. Atmospheric chemistry refuses drama but rewards accounting. With little hydrogen and modest CO2, the dominant infrared opacities pivot to rock vapor traces during hot flashes, CO, metal oxides, and to continuum from small silicate grains otherwise. He I-10830A, a tracer of upper atmosphere escape, remains undetected across stacked transits, if any, and superior conjunctions, pressing the escape parameter lambda high. The constraint loops back to surface gravity and hence to interior models. Your best-fitting composition has an iron-rich core and an olivine-leaning mantle. The stagnant lid regime, if real, implies a thermal evolution where outgassing arrives in pulses rather than a continuous breath. Life, in such a laboratory, would have to be a chemist of margins, poor-scale communities that harvest redox at fracture interfaces, metabolisms content with scarcity, biosignatures that resemble geosignatures so closely that distinguishing them would require isotopes beyond current reach. Non-detection here is not emptiness, it is a bound on how loudly chemistry can speak without biology's megaphone. Noise is a character you learn by name. Instrumental systematics pretend to be planets until decorrelated. Stellar flicker pretends to be weather until seismology constrains granulation, scattered light pretends to be dust until roll-angle systematics confess. You cultivate cross-checks that punish coincidence, a phase curve amplitude consistent with the eclipse depth, a polarized crescent peak consistent with the thermal inertia, an RV semi-amplitude consistent with the density implied by seismic radii. Where they disagree, you widen your priors before you tighten your claims. Where they agree, you allow yourself a figure that plots not a discovery but a reduction in uncertainty, a more honest currency in an archive defined by restraint. Even the galaxy's quiet is punctuated by maintenance. X-ray ripples and faded radio lobes testify to AGN feedback that still cycles, an interval timer that prevents catastrophic cooling. Old type Ia supernovae occur at a rate you can predict from stellar mass, each injects energy and iron, each slightly perturbs the hot halo, each barely registers in the optical but registers all the same in the entropy profile. Over the next few hundred mir, your models forecast no phase transition in the halo's thermodynamics, red sequence membership is secure. The cluster will lose stars to evaporation, their debris will paint faint, long arcs you can chase if you refuse to age out of the project. The planet will spin down imperceptibly, its ring, if real, will rarefy, its haze will thicken and thin like a tide governed by meteoroid weather. By then, the virtue of the system will have become obvious even to those who crave fireworks. It lets you turn small tools into big truths. You learn how bottom-line planetary physics behaves when star formation has ended and the galaxy's only drama is memory. You learn how halos hold themselves together without the confusion of spiral arms and cold flows. You learn how clusters age when their environment has the decency to be simple. None of these are showpieces, all of them are durable. The amber light was not an aesthetic choice but a data structure. Read it long enough and it becomes a language in which endurance, not spectacle, is the headline. Think smaller still, down to the units that stitch your inference together. Error bars are not decorations, they are state variables you evolve. For radial velocities, you partition the variance into photon noise, instrumental drift residuals, telluric modeling error, and stellar p-mode leakage. Each term gets its own hyperparameter and a time kernel that knows weekends from winters. For thermal phase curves, you separate intrapixel response from pointing jitter, thermal breathing from zodiacal background, then let a Gaussian process kernel with a physically motivated timescale, the spacecraft's heater cycle, mop up the rest. Polarimetry earns a forward model of instrumental Mueller matrices that change with focus and temperature. You marginalize over them rather than subtracting a best estimate. When the posterior narrows, you know which nuisance shrank and why. Formation histories for ellipticals used to be morality plays, monolithic collapse versus mergers, until simulations taught nuance. Your object's photometry and kinematics favor a two-phase tail, an early, dissipative build that forged the compact core and locked in alpha enhancement, followed by dry accretion that puffed the outskirts and diluted gradients. You see its footprints in the outer stellar halo's metallicity scatter, in the mild radial anisotropy that rises beyond 1 to 2 Ri, in the boxy isophotes that betray triaxiality. Shells in the deep image are not a painting trick, they are phase wrapping, stars released on radial orbits during minor mergers, their density caustics marking epicenters like tree rings. Count shell spacings and you can date the last significant accretion, feed that into the cluster tail modeling and the galaxy's potential becomes a consistent stage set for every actor on it. The globular's multiple populations are chemistry lessons wearing gravity's uniform. Sodium-oxygen anticorrelation maps to proton capture processing in a first-generation's massive stars, helium spreads reveal pollution routes, aluminum and magnesium dance to the same tune. Spectroscopy of turnoff stars avoids evolutionary mixing and keeps the story clean. You use those fingerprints to tag field stars in the halo as former cluster citizens. Their spatial distribution, weakly flattened, radially extended, supports a picture where clusters both form and dissolve in episodes, seeding the field with stars that remember a clan long after the clan has evaporated. Blue stragglers pad the clock, their apparent youth a dynamic artifact, their radial profile, centrally peaked in mass transfer-rich clusters and flatter where collisions rule, gives you a knob to tune the cluster's dynamical age independent of isochrones. Return to the super-Earth and push on surfaces. Regolith is a verb here, rocks comminuted by tiny impacts until thermal inertia and albedo co-evolve. Laboratory spectra of powdered basalts and lunar glass under vacuum reproduce the 8 to 13 m emissivity features you glimpse after shower events. Grain size distributions inferred from fits prefer radii less than or equivalent to 0.3 m, drifting larger for a few months post-storm as sintering and electrostatic clumping proceed. If you fold that microphysics into a 1D boundary layer with a diurnal skin depth tuned by thermal conductivity, your phase curve offset and amplitude stop being free parameters and start being consequences. The night side never plunges to the radiative limit because heat leaks through a few centimeters of material that refuses to be perfectly insulating. Your best fit conductivity is within a factor of 2 of compacted lunar soil. Magnetism is the rumor worth chasing even when silence persists. A heavy rocky planet with a large core can power a dynamo if core cooling outpaces the mantle's thermal choke. In a stagnant lid world, that is a tall order, unless mantle overturns occur. You define an observing program that pairs low-frequency radio campaigns, tens of megahertz, designed to catch cyclotron maser emission, with mid-IR monitoring sensitive to resurfacing pulses. A flare of radio power within a year of a thermal brightening would be a smoking gun for core mantle coupling events. Non-detections across a decade still by physics, upper limits on the planet's magnetic moment push you toward either sluggish core cooling or sulfur-rich cores whose conductivity throttles dynamo action. Both pathways feed interior models and, via escape, the present sky's meagerness. The star becomes a metronome for everything else. Seismic large separations and mode envelopes give radius and mass, rotational splittings give inclination, the combination turns V sin I into a true period. Chromospheric indices, Ca2HK, H-alpha, He10830A, map a cycle whose amplitude is small but coherent. You decorrelate RVs with these indices and watch the planet's semi-amplitude stabilize, the mass estimate departs the realm of plausible and enters the realm of precise. In the near IR, molecular lines crowd the spectrum, cross-correlation against CO and H2O templates hunts for any whisper of retained volatiles. Silence here is also a sentence, a planet above the gene's parameter threshold, below the mini-Neptune volatile fraction, sitting in the sentence we call rock. Distance and mass are remeasured until boredom equals confidence. Tip of the red giant branch distances in the pristine halo fields tie to surface brightness fluctuations in the bulge, peculiar velocity corrections get a prior from flow models, you reconcile everything within a few percent. Lensing shear stacked over a control sample of twins supplies a halo concentration prior, your galaxy lands near the median, cored softly within 1 kpc. That core, echoed by the stellar light central flattening, prefers a story where black hole scouring and feedback both contributed. You point a deep, low-frequency radio array at the nucleus, a flat spectrum, sub-MJY core mumbles, old bubbles now ghosts in X-rays, doing PDV work long after the choir left. Your pipeline grows teeth. You run fake planets through the RV code, fake hazes through the transmission retrieval, fake rings through the polarimetry, and measure how often you lie to yourself. You publish the null tests with the detections, you make your corner plots boring. The planet's density sits on the rocky line with a plus or minus 5 to 8% half-width, the albedo prefers a low number with a fat tail, the thermal inertia lands where rock lives, the polarimetric peak declines gently with wavelength as sub-m grains should. Individually, each is modest, together, they triangulate a world that is exactly what a super-Earth under a quiet red star in an old halo ought to be, and that exactness is the discovery. Predictions are the courtesy you pay reality. You forecast a modest deepening of the 10M feature in 7 to 10 years if the micrometeor calendar you inferred from debris dynamics is right. You predict a millimagnitude surface brightness fluctuation change in a background galaxy when a globular tail caustic slides over it within a decade, and you book the time now. You commit to a radio silence threshold. If cyclotron lines do not appear after the next predicted resurfacing pulse, the dynamo hypothesis loses a rung. You flag a parameter that will move least, the galaxy's outer metallicity gradient should remain flat within uncertainties unless a new minor merger injects fresh stars. If it steepens, something dynamical happened, and your shell dating will need a footnote. Why bother with a system that refuses spectacle? Because restraint is a microscope. Spirals confuse by construction, bars torque gas, arms shock clouds, star formation rearranges opacities hourly. Here, the galaxy is a kinematic textbook, the cluster is a clean n-body sandbox, the star is a seismology beacon, the planet is a laboratory for rocky climate without the distraction of deep volatiles. You are measuring endurance, how physics writes long records when noise sources are minimized. The amber color is population synthesis in plain view, the globular is a ruler that carries its own ticks, the super-Earth is a control experiment for regolith, haze, and heat. And still there is room for surprise. A low-luminosity AGN flare could briefly light up coronal lines and drive a gentle wind, a stealthy infall of a cold cloud could seed a spasm of star formation that dies in its cradle, a resonant overlap in a faint debris belt could trigger a comet year that you would watch rewrite the planet's 10M spectrum week by week. You do not count on these, you plan for the possibility. Meanwhile, you keep collecting the slow variables, dispersion profiles, polarization arcs, eclipse depths, mode splittings. Pages accrue. The archive thickens. In the end, the promise is simple, a full-stack inference of a quiet corner of the universe where every layer, halo, cluster, star, planet, constrains the others until what remains is not a story but a measured ecosystem. The galaxy's gravity field predicted by globular tails matches the one the star feels, the star's age and chemistry predict a rocky planet that the RVs weigh, the planet's surface physics explains the curves you watch swing with its orbit, the absence of gas in the galaxy explains the quiet that makes all of this possible. You set the dataset down and realize that amber was never only a color. It was a preservative. It kept the physics legible long enough for you to read it aloud. Comparative context sharpens the edges of what you have. Put the super-Earth on a ternary diagram of bulk composition, iron core, silicate mantle, volatiles, and watch the posterior huddle along the iron silicate edge with negligible third component. Density alone cannot separate a large core from a dehydrated mantle, so you borrow the star's abundance pattern as a prior on building blocks, mg/Fe, c/Fe, and care of bound interior mineralogy and limit how extreme the core fraction can be without violating refractory budgets. An olivine-leaning mantle raises the solidus and shifts convective vigor, a pyroxene-rich one does the opposite. You forward propagate these differences into observable thermophysical parameters, thermal inertia, day, night offset, eclipse color temperature, and discover that the data prefer the stiffer, higher solidus branch by a hair. It is not dramatic, but it is directional, and with another season of phase curves the direction may become a step. Dynamics of the wider system set the cadence of accidents. Long-term integration with a smooth, triaxial galactic potential and a modest, parametric debris belt shows secular resonances sliding slowly across semi-major axis space as the planet and any unseen neighbors exchange angular momentum. The flux of comets into the inner system scales with the gradient of these resonances. You calibrate that gradient against the observed frequency of mid-IR brightening events and back out a belt mass that still evades direct detection but must exist if the spikes are real. The same integration predicts that pericenter glow in the far IR would track a mere beat pattern. You cannot see that beat, but publishing it turns a speculation into an eventuality someone else can check. Instrumentation extends the reach without changing the philosophy. A stabilized, fiber-fed NIR spectrograph with simultaneous calibration pushes radial velocity precision into the low m/s regime on cool dwarfs, thermal infrared imagers with stable point spread functions and decorrelated intrapixel response make 10 to 15 micrometers eclipse photometry repeatable enough to stack dual-beam polarimeters that rotate modulators fast relative to seeing freeze-out atmospheric variability on the ground. None of these deliver cinematic plots, they deliver residuals that behave. The pipeline's priors mature from broad and fearful to informed and conservative. Cross-validation with injected signals keeps the appetite for detections on a leash. The galaxy's outskirts continue to confess under pressure from resolved stellar techniques. Star counts in the most tenuous fields yield a metal-poor tail to the halo distribution function, fitting those with accretion models pegs at least one progenitor at low mass with an extended, quenching late history, just the kind of donor that would bring in a cool dwarf like your host. Shell spacing analysis dates the last minor merger to a few gyre, globular tail orbital fits land on the same timescale. The consistency is not inevitable, and its presence prunes a third of the assembly histories you might otherwise entertain. Weak lensing shear around the galaxy, stacked with a dozen analogs, returns a concentration parameter consistent with a halo that had its baryons heated early. The hot X-ray halo's entropy profile agrees. The red sequence is not a slogan, it is a thermodynamic state with multiple, testable witnesses. Noise that would bury a louder planet becomes legible here. Granulation noise in the host star is red but small. Asteroseismic modeling turns it into a prior on RV jitter, shrinking the amplitude error bars. Telluric residuals in the NIR are modeled as an external state vector, a basis of wet column, temperature, and wind parameters measured by auxiliary sensors, and their projection is removed before any planetary signal is hunted. Photometric drifts are decorrelated against spacecraft telemetry rather than against the light curve itself to avoid eating the signal. The cost is a more complicated covariance matrix and the benefit is honesty. You report upper limits when limits are the truth. The paper's figures favor residual plots over glamour shots. Interiors keep translating chemistry into heat flow. A thicker, stronger lithosphere under a low volatile sky forces stagnant lid convection punctuated by delamination events when eclogite develops at the base of overloaded crust. Each delamination episode dumps dense rock into the mantle, triggers short-lived decompression melting, and refreshes the surface with basalts whose glass content controls emissivity near 10 micrometers. The recurrence interval depends on mantle water, trace, radiogenic inventory, modest, and tectonic inheritance, unknown but bounded by the lack of large secular drifts in thermal phase curves. If an impact garden dominates regolith evolution, glass abundance will rise after showers and decline as micrometeor abrasion repowders surfaces. Time-lagged correlations between meteor shower windows and mid-IR features already whisper this story. Magnetism either appears in brief windows or not at all. A sulfur-bearing core raises electrical conductivity and can throttle dynamo action unless CMB heat flux clears a threshold. In a stagnant lid planet, that threshold is crossed only after major overturns. Low-frequency radio campaigns scheduled around predicted resurfacing pulses target cyclotron maser lines near the planetary gyro frequency. Non-detections shrink the magnetic moment prior and push interior models toward either faster inner core growth, if any, or compositionally stratified cores that resist convection. Even negative radio space carves physics into shape. The globular cluster's microphysics shows up in macroscale predictions. Mass segregation steepens the inner mass function, evaporation flattens the outer one, together they set the tail's surface brightness profile that you match to observations. Internal rotation leaves a subtle twist in isophotes. You detect it and fold it into orbit libraries, slightly narrowing the galaxy's allowed triaxiality. Blue straggler radial profiles tell you whether collisions or binaries dominate. Your cluster lands in the mixed regime, implying a core density that agrees with millisecond pulsar counts. These crosschecks are not ornaments, they are anchors that keep the galaxy's potential from drifting while you weigh a planet 100,000 light-years away. At system scale, the absence of neighbors is its own dataset. High-contrast imaging around the host star down to a few AU finds no Jovians bright enough to have sculpted the inner architecture. Long baseline RV trends are flat within a meter per second per year. Transit surveys return null, implying low geometric probability or a scarcity of compact multiples. Formation in a low metallicity, accreted dwarf followed by emigration into the elliptical's halo can yield exactly such sparse systems: few giants, a handful of rocks, no resonant chains. The planet you study may be alone enough that its history is legible, unfogged by later crowding. The meta-inference is the prize, a closed loop where galactic assembly, cluster dynamics, stellar evolution, and planetary climate constrain one another rather than living in separate papers. The galaxy's mass profile from tails sets the gravitational tides in the system. Those tides set comet flux. Comet flux modulates haze and thermal spectra. Those spectra constrain interior cooling. Interior cooling sets whether a dynamo lives. Radio silence or noise flows back to atmospheric escape. Escape rates feed into chemical budgets. Chemical budgets translate into the planet's albedo and thermal inertia. Those feed back into the phase curve that, when modeled, prefers a regolith. Consistent with micrometeor gardening predicted by the comet flux you started with. The circle closes without hand-waving, and the uncertainties shrink around values that cohere. You can keep cleaving reality with this patient blade. Deeper X-ray exposures will constrain the entropy floor and the AGN duty cycle more tightly. Time-resolved spectroscopy across secondary eclipse will separate a silicate continuum from any transient line forest. Longer polarimetric baselines will watch the crescent peak wander with suspected rings or obliquity. Extended kinematics of faint halo stars will pin the outer potential and either confirm or kill the mild core. Every addition is incremental. Cumulatively they turn plausible into measured. The arc